should probably. Yeah. Okay, let's do it. All right.
Awesome.
And I see that we are a few people. So this is the opportunity for interaction if you want. If you've given talks, well, it depends on the people, but I really like to be interrupted and answer questions if you have any or anything. So I would like this to be a conversation because it's going to be technical, a lot of technical stuff about the instruments, and I don't want it to be too much arid, extra dry. So if you have questions, anything about James Webb doesn't have to be about instrumentation, but time proposals, anything, you can please raise your hand. Um, and before I start, I would be curious to know if first, if any of you has used web, or if any of you is interested in particular instruments with web. So if you have never used web or are not interested in particular instrument, maybe knowing what science you're doing will help steer towards a few modes that I'm going to talk about. So if you don't mind, I'd like just to have a quick turntable, round table to know what's the area that you're working in and if you're interested in web and what instruments. Okay, so first let's start with Jess.
All right. I'm in the field of protoplanetary disks, planet formation. I'm interested in imaging, I would say, with JWST, maybe NIRCam, maybe near-gram chronographic imaging, maybe imaging with MIRI. I'm not sure. I've never used it before, but we're very keen to try and directly image planets that we think are embedded in disks. So that's where I'm coming from.
Okay, okay, great, thanks. The next one I see is Solveig.
I'm using James Webb data from near spec and IFU mode for my PhD.
Okay. And for galaxies, I suppose?
Yeah, we're using it to search for central black holes in ultra-compact dwarf galaxies and like nuclear star clusters in the Virgo galaxy cluster.
Okay, makes sense. Then I don't see the other people. I see Isabel, Sander, but well.
Hi.
Hi.
So I mostly work in like high energy X-ray analysis.
Okay.
Um, but in terms of JWST, I would say probably the synergy with more X-ray telescopes. And um, I work specifically in pulsar wind nebulae and supernova remnants, so imaging complicated diffuse sources like that.
Okay. Okay. And Adrien, what's your
Yeah, I was writing in the chat. So I am working on AGN variability,
okay?
and unfortunately, I am not currently using James Webb data, even though I wish, because it's really awesome data. If I were, if I was given the chance to get some data from one of the instruments of James Webb, I think I would try to get some images
Mhm.
from some of the AGNs I'm trying to study. In particular, I'm interested in the low mass AGNs and trying to use variability as a new method to find potentially uh, intermediate mass black holes inside the galaxies.
Okay, interesting. And I don't know if we're missing someone or not. I can't tell. But yeah. Okay, well, thanks very much for sharing this. Um, so all right, so I'll try to think about that when I talk here. So let's start with this movie that was Ariane 5. just as it let James Webb go into space. And this was an amazing moment. And the deployment of the solar panel in particular was the omen of a great success because it ensured that we got energy for the telescope. Another great thing that happened here is the velocity that Ariane 5 gave Webb. It gave a perfect velocity, perfect direction, which meant that there was no, or essentially almost no course correction, which means that we kept all of the fuel unused and available for making the lifetime of Webb longer than expected. So we were expecting 5 years, and thanks to Ariane 5, it's now 20 years that we think the observatory will last. So that's a big difference. I was not even aware of that and I was in the project until after the launch. And so yeah, I'm Loïc. I've been working on this project for since 2010 essentially, in Montreal, at the University of Montreal. So I got the opportunity to work there to design, test, prepare with pipelines, and now using data for the nearest instrument. The nearest instrument is the Canadian participation to Webb. Canada's participation is split in three parts. The Canadian Space Agency is providing the funding, very important, the biggest astrophysical project ever for Canada. Honeywell in Ottawa is the contractor. So it's an aerospace industry in Ottawa. They actually built the nearest instrument. And I should say nearest/FGS, and I'll talk about this in a moment. And finally, University of Montreal is the science like head of this. It's thinking about what kind of observing modes we needed for nearest and FGS, and we're still involved in the calibration and continuing with the operation. So FGS and TFI. So this is our Canadian instrument. On top, you have the defined guidance sensor. It's the guiding for Webb is very important. Every science observation starts with guiding. And so early on, we thought, hey, we could put something on the backside of this aluminum plate and a science instrument. And this was then the tunable filter imager. It was built by Honeywell. Unfortunately, in 2010, when I joined, and there was 1 year left before delivering to NASA, tests demonstrated that the instrument was not working. It was not working. So in a hurry, we had to reshuffle things, keep most of the hardware, but change a few optical parts and create a new instrument called NIRIS. And so that's why now it's NIRIS. That's for the history. But so James Webb was launched on a sun orbiting orbit at the second Lagrange point, and it orbits this in about 6 months. And so the telescope is in the shade. It's always in the shade. That's how we can cool the detectors and the optics, and that allows to reach a very cold temperature. And it also means that the pointing of the fields on the sky is constrained because of this orbit and orientation. So yeah, so at any moment you have a few angles of degree of leeway. You can move one axis between 85 and 135, and that's the mostly leeway we get, and that allows us to access a part of the sky, the what we call the field of regard. There's another leeway on the other axis, plus or minus 5 degrees. And so, yeah, so those are the movements we can do with the telescope. So it defines the field of regard, which is roughly it's the region where we can observe, conduct observations safely. this field rotates over the course of the year by 1 degree essentially per day. Um, um, Over time, the analyst sweeps over the entire celestial sphere. It actually does it twice because it's symmetric every 6 months. And so it gives us access to the whole sky in 6 months. So typically, any target that you're going to observe is going to have 2 windows of observations in a year. Um, Here is the field of view at the focal plane of the telescope of all the instruments that we have. So there's a NIRCam, the imager, the center, close to the optical axis for best imaging quality. The guider is at the bottom. It has actually a spare guider. It has 2 guiders, FGS1 and FGS2. So both are functional. We're using one, or depends on the stars available in the field. We use one or the other. And you have NIRIS, MIRI, the mid-infrared instrument, and NIRSPEC that's rotated a little bit. So yeah, so those are the instruments, and they're not all imagers, but here are actual images. So NIRSPEC is actually able to take images as well if you open the slits and don't put any grading. So yeah, that's it. The field of view, or the field of view of all the instruments is not fixed on the sky, right? As you rotate on your orbit, the orientation will shift, will turn, and so depending on the type of imaging, if you want to mosaic, say, some targets have limitation in terms of angle that you can access, and if you want to do spectroscopy or MOS, multi-object spectroscopy, the rotation angle is important to take into account. All right. So I will skip a few things here. So here we have the ISIM, so the instrument module. Of course, before launch, as it was assembled. So the FGS NIRIS is at the center of this ISIM module, and the other 3 instruments are mounted as shown. So the NIRCam is the imager between 0.6 and 5 microns of wavelengths. NIRSPEC is the spectrograph, same near-infrared coverage, and it can do multi-object spectroscopy. MIRI is this special mid-infrared instrument, unique of its kind on the James Webb suit. It goes from 5 to 28 microns with both imaging and spectroscopy. MIRI is the instrument that requires additional cooling. The other ones use passive cooling in the shadow of the solar screen. MIRI actually has a cooler on top of that. And so I would say it's the instrument that's the most fragile and that we'd better use as soon as we can, not delay until we use it, make most interesting observations with it as soon as we can. It may be the first one to fail, or maybe it will stay forever. I don't know. We'll see. All right. So combine all those instruments, give you access to, last time I checked, 17 different observing modes. So there's no way I'll be able to describe all of the modes today, okay, in details. I'll regroup them in a few instruments offer comparable modes that I will talk about. Yeah, so that there's a lot to digest here in terms of observing modes. Any questions so far? By the way, I'm not monitoring the chat, so maybe I should. Okay. All right, so let's go with, yeah, so here you have for the imaging mode. So I'll cover, you see at the top, I've grouped observing modes together, and these are the categories that there are. So we'll start with imaging. Imaging can be done with 2 near-infrared instruments, NIRCam and NIRIS, and 1 mid-infrared instrument, MIRI. Okay, and so within imaging, there's coronagraphy that I was going to talk almost at the last step a little bit. Yeah, but essentially, yeah, I'll come back to it. Just briefly mention those. So there's also a spectroscopy available across the wavelength range from 0.6 to almost 28 microns or so. Each instrument has some version of spectroscopy, be it long slit spectroscopy, multi-object spectroscopy, or integral field spectroscopy. So again, MIRI is the only representative of longer wavelengths. Multi-object spectroscopy is only done by NIRSpec. It has a special MSA, so the shutter array, the I guess, multi-shutter array. Sorry, I forget. MSA that can open and close shutters to take long slit spectra across a field of view of about 2 by 2 arc minutes. It also has fixed slits and larger aperture for different other modes. Integral field spectroscopy, also called IFU, integral field units. Two instruments have that mode, NIRSpec and MIRI. So essentially here you're getting an image and spectra of order like 1,000 spaxels. So essentially you can have like a small field of view, maybe 3 by 3 arc second field of view, and in that field of view you get spectra for everything. So that's good for, say, AGN at at large distances, and you want to study the structure in the AGN, for example. That would be potentially a good mode. The next mode is the wide field slit-less spectroscopy. In this case, we don't have shutters, we don't have masks, and we actually take spectra of everything that's in the field. It makes for a very crowded spectra, many overlapping spectra, so it can be difficult to analyze and do the data reduction, but potentially it can yield a lot of observation, and typically there are orthogonal disperser, one that will disperse in the horizontal direction, one in the vertical direction, as well as taking images. This in total can help you, decontaminate some of the overlapping spectra. So you have two instruments that do WFIS. You have the NIRIS at blue wavelengths, less than 2.5 microns, and NIRCam at redder wavelength up to 5 microns. And also, we don't forget the solar system. So there is a complex way of defining moving targets in the solar system. And so it's crazy what you can define as targets. You can define moons moving in the reference frame of the planet orbiting the sun. You can there are multiple ways of defining moving targets, and you can, of course, observe everything that's past, I guess, the moon and past, essentially Mars and beyond. All right, so that's your field of view. It shows up to 5 instruments, and the obvious question is can we observe all instruments simultaneously? The answer is, in principle, we can. In practice, in reality, we allow parallel observing, but 2 instruments at a time. And in that case, you will not observe the exact same target. You'll be observing in the focal plane at different positions. So you'll be a very good example is observing a deep field region like a Cosmos field or a deep field, a Hubble deep field, and taking WFIS spectra while you do imaging with NIRCam and WFIS with NIRIS, and then you can get spectra of some region and imaging of other regions of the deep field. All right. And finally, the time series observation, referred as TSO. Uh, this is, a mode that's in high demand by the exoplaneteers. So that's when you essentially monitor transit of exoplanets to get spectroscopy of the atmosphere of those exoplanets. And every instrument has a TSO mode available, although some instruments are more used than other in that mode. So NearSpec and NIRISS are the most used for the TSO. All right. So, and I think, and okay, there's a new mode as well available for TSO with the NearCam instrument. I'll guess I'll talk about it later if time allows. Right. So quickly, okay, each instrument, their capability, MIRI, mid-infrared, can do imaging with 10 filters, as low resolution spectroscopy at RF of 100 between 5 and 12 microns, as medium resolution spectroscopy, also the IFU, from 5 to 28 microns, and has coronagraphy available. NearCam is doing it's your workhorse instrument in imaging, as two channels for each of the two field of view. There are two channels, one red and one blue. It has wide field slitless spectroscopy and coronagraphy imaging, as well as time series. NearSpec works below 5 microns as the micro shutter array. So to do MOS, can do IFU imaging, high contrast single object spectroscopy, so long slit spectroscopy, and as a TSO mode. And finally, NIRISS, has three modes. One is the wide field slitless spectroscopy, the single object slitless spectroscopy, that's the TSO mode, so the exoplanet mode. And aperture masking, which is so it's an interferometer. So James Webb's AMI mode on NIRISS is your space interferometer, and can all do imaging. All right. So how does that work typically? Okay, so let's switch gear a little bit from each instrument. I'll go in even more details, hopefully more slowly a bit later. But before I go there, I'll describe you a typical sequence before you do a science visit. Okay, so the first thing is that the telescope knows it's pointing mostly based on the star tracker. The star tracker is proprietary knowledge from, I guess, Northrop Grumman. But essentially, it's three telephoto lens looking at bright stars with a wide field of view and making sense of that to know where it points. And it actually has a very good accuracy only with the star tracker of better than 1 arc second. So you can go and point blind to a better than 1 arc second accuracy. That's really good, really, really good. And then the next step, once you slew, so you slew your telescope, it takes 15, 30 minutes, and then you're at your field and you want to initiate guiding. So it's always what happens. The FGS starts with taking as wide a field of view, single image, identifies the predetermined guide stars that it was expecting in the field, picks the one it wanted. Then it starts a readout in the AC mode, taking a smaller subarray read, which means it can read faster and at a better rate and get more images and centers that star. And then it reads an even smaller subarray around that position and goes on. So there are three stages, and the final stage is the fine guidance, which uses an 8 by 8 pixels only. And then it will declare its guiding, and it will take like 64 millisecond exposures forever. You've had observations that have lasted more than 2 or 3 days already. So it always takes images and ensures that the star remains centered. So this is a bit of a, where the pride, the Canadian pride, where Canada is always keeps always an eye on the sky with the FGS. Yeah, it's what we do. Okay, so the next step after you've initiated guiding is to do the target acquisition on the science instrument. So we started guiding, the instrument can now start doing its thing. So yeah, let's go straight to what happens. So I have the example here for NIRIS. The first thing we do with it, the instrument is take an image, and we should be roughly centered on our target by then. So we take an image with a small subraster, and the step two is to actually scan that image to detect the star or the target and do a centroid on it to measure its position and send an adjustment to the fine steering mirror so that we get the target where we wanted it to be. So apply the correction, and that's it. Then we can say, okay, the target is exactly at the sub-pixel position where we expected it to be, and we can start taking long exposures. Another note is that if you have observations with webs, there are an observation, especially say for mosaicing, can be split into different visits if it's so large that you need to reacquire a new guide star. So you don't need to read all of this slide, I guess. You just look at the picture. There's a circle. That's your visit splitting distance. If the movement you do from the science instrument is too large, the guide star will get out of the FGS field of view and you'll need to reinitiate guiding. That's a detail. Okay, so at this point, it's already like been 27 or so minutes. I can go deeper into more details in each of the modes. So I've heard imaging, coronography, IFU with near spec. Have I heard like MIRI? Yes. Okay. So let's do the easy stuff first. Let's do some imaging. This is NIRCam. This is your workhorse instrument in the near infrared, and so it has NIRCam has a dichroic, which splits the blue light and the red light in two parallel paths. And on top of that, NIRCam has two field of views. So if you concentrate on module A has two channels, a red and a blue. So everything that's shorter than 2.5 microns is the blue, and above 2.5 is the red. And the squares you see represent the detectors on which you do the imaging. There's more detectors for the short channel because the PSF is smaller, so you need the resolving power. And on the red, it's coarser, so one detector is enough. And so you can observe it has a field of view of 2 by 2 essentially. NIRCam has quite a few filters, but mostly wide and medium filters, few narrowband filters. And that's for the history. That's because the imaging with narrowband filters initially was supposed to be done with the TFI mounted in NIRCam. So the TFI instrument, the Canadian instrument, used to be a component of NIRCam that was going to produce narrowband filters. It got ejected from NIRCam, and that's why we wanted to do a Canadian instrument with it. But so there's less narrowband imaging with NIRCam than you would have maybe liked. Yeah. So for MIRI, the mid-infrared imager, well, you see you have imaging between 5 and 30 microns. The field of view is a bit smaller. because the one detector used for that is very busy. You have the imager on the right-hand side, and on the left you have the coronagraphy channels. And so when you take imaging, you have like a rectangular image size. It's a different technology than the detector is different technology than the near-infrared detectors, but suffers from some of the same problems, charge migration, for instance, and yeah. Yeah, so I think that sums it. Nearest also has an imaging mode. It's really a spare or is used for parallel observing. It has the same wideband filters, most of the wideband filters of NIRCam. So it's a spare in case NIRCam dies. All right, and we do in imaging we do dithering, not we don't stare, and that's why? Well, it's to fill gaps between detectors due to bad pixels and get better cosmetics out of those moves, and also to oversample the PSF and achieve better sampling. To also enable background construction and subtraction for MIRI, for instance. Dithering is standard when you do imaging, but also long slit spectroscopy. You do dither along the slit. And staring is used for time series observation. So there's no dither when you do time series because you want maximum stability and best accuracy. Here's an example of the dithers available for NIRCam. There are many available dithers. I will not go through them. It's just to give you an example. On the left is the large primary dithers that cover large area surfaces. And on the right is subpixel, is if you want to resample your PSF finely, you can do very tiny moves to do that. You can do mosaicing with NIRCam. In this case, you would use both channels of NIRCam, A and B, so that you get maximum field of view, and you would move the telescope on different visits to cover the whole galaxy or some part of the galaxy. All right, and as a side note here, I've been talking about detectors a little bit, but if you ever if you ever did a time proposal with Webb, you have to deal with detector readouts. So maybe understanding how it works is important. So near-infrared detector, you have to know that we don't have a shutter in the near infrared. Okay, it's not unlike CCDs and optical instruments where you have a physical shutter stopping the light. There's no shutter in near infrared instruments. It's what we do is that we reset the detector, and as soon as we reset, it starts receiving photons, and we read the detector continuously, and it doesn't displace charges like in the CCD. The charges remain there when we read, and we keep reading until we reach some saturation or we end the exposure. And how we read is that each pixel is read consecutively, starting from pixel 1 up the first column and starting on the first pixel on the second column and up and so on. And so it takes about 5 seconds to read out the full detector or actually reset it. We also reset it the same way, pixel by pixel. And so after the first read of the full detector, we come back to the first pixel and start again. And so it takes time. And so that sets our minimum exposure time. If you're observing a very bright star, you may saturate during a 5-second exposure. So you want to use a smaller subarray that's depicted on the right-hand side, which you can read faster because you read at a constant 10 microsecond per pixel rate. And so that's why there's a lot of use of subarrays in James Webb because you read out a smaller section, say, of a spectrum, and if you wanted to read it faster, you need to read a smaller amount of pixels. And a pixel is nonlinear, so an ideal detector will have the response linear with the exposure time. In reality, it's nonlinear and it reaches a saturation, the full well. And also, for most purposes, you should aim to not go beyond 50% full well because then there's charge migration effects kicking in and bringing systematics errors or problems in your signal. So you try to keep within like 50% of full well. Yeah. And there's also like a jargon that we use with Webb in terms of what we say is a read is actually a group of reads. Obviously, reading and keeping all of the individual read can take up a lot of disk space on board, so we cannot save everything. So to save space, we average reads together and save the average and send this to ground. Or we can even skip some of the reads. So think of a group as a read mostly, and the integration is this ramp until we reset, and you can stack many integrations together in an exposure. So that's for the jargon of James Webb if you ever have to write a proposal and go through the exposure time calculator and the astronomer proposal tool. All right, so I have some slides on spectroscopy that I can share. The typical, this is your sketch of, an instrument that's doing spectroscopy. You have your source light coming from the left, going on the telescope, being focused on the image plane, and then getting to the instrument where a parallel beam is formed, where you put your disperser and you get a spectrum projected on the detector at the right. So that's fine if you have a source and nothing else in the field, that works. You have a spectrum. If you have a second source, this second source spectrum will get projected onto the detector, maybe contaminating the first one. So they will overlap if you have several sources. So to prevent contamination, overlapping, we put a slit, a narrow slit, and this will prevent any light except your target light from forming a spectrum. So so in the mode where you do the wide field slitless spectroscopy, you do not use a mask and you take spectra of everything that's in the field of view. I think, briefly skip those because that's not the main mode I think people were going to use. You can do long slit spectroscopy or MOS spectroscopy with NIRSpec. For MOS, with the microshutter array, you put long slits at several positions where you expect a source and you get spectra on the right. And so the device that does it for NIRSpec is the MSA, the microshutter array. It's a high technology. It's a wonderful technology that was deemed risky, but works. In blue, you have the microshutter array. On the right, if you zoom in, you have those flap that open and close when you pass a magnetic arm, and so you can control if it's open or closed, and that's how you dial in the positions that you want to take spectra from. There are also fixed slits in the microshutter array at the center, and even an opening for the IFU, so to get the light in. You'll see the other slits are in green or here in black. And so you have also a big aperture, a square that's for your time series. Okay, so for exoplanets. So those are available as well if you only want to take one spectrum at a time. Okay. So I've talked about this, and here's your typical image. If you take a multi-object spectroscopy, you get lots of spectra. That's with the prism of the NIRSpec. Another example, another image is where you position your slits. And so typically we open 3 microshutters to form one slit, and we dither at 3 positions in that long slit. The use of blocking filters in spectroscopy, well, it's kind of optics 101. Orders when you diffract the light with a grating, it will form orders and they will tend to overlap. So order 1, 0, -1, and 2. Between 1 and 2 here, there's an overlap. So you use a filter to block some of the light and effectively reduce the length of each spectra and prevent contamination. So that's why we also have blocking filters combined with gratings for near spec. So here near spec has several gratings, a prism, so resolving power between 1,000 and 3,000 for the gratings, and the prism has much lower resolving power. A lot to choose from. So I talked about the fixed slit observations. You have slits that you can use. In terms of observing strategy, you can dither along the slits. So on the left, I guess you have either no dither or 2, 3, or 5 positions. Most people, I think, use 3, I believe. You can also dither along the spectral direction, left, right, if you want to have, I guess, slightly improve your resolving power. And you can do both. In terms of mid-infrared spectroscopy, you have MIRI again, and it uses a slit at the bottom right. You see a slit that's for your LRS, low resolving power, low resolving power spectroscopy between 5 and 12 micron. There's a square MRS, a pink square dead at the center of this slide, and it shows that the field of view of the MRS for MIRI is at a different location and projects onto actually 2 other detectors not shown here. So the MIRI LRS, I'll spare you all of the details. You can get them online, but it's a low resolving power. It's used quite a lot. It's one of the modes of MIRI that get used a lot because it takes spectra, in the 5 to 12 micron range where you still have photons coming from stars. You're not photon starved too much. Okay, finally getting there, the integral field unit spectroscopy with James Webb. So you have 2 instruments, NIRSPEC MIRI, that have those capabilities. So the integral field in my sketch, in my sketch world, it's essentially you replace a slit with a type of mirror, a slicer, an image slicer that actually slices your image into several slices and reorients them into a single long slit, very long slit, and projects onto the detector. So for each position, each slice of your image, you get a spectrum. And each slice of your image is several pixels. So it's the height of your image. And so there's that for NIRSPEC, for MIRI. And here's an example of how it looks on the detector. So if you have your image at the bottom left, that's what you're studying, say in AGN with lots of structure, and each of those squares are pixels, sure, but we call them spaxel because they also have spectroscopic information. I believe I have some, yeah. So if you take the first slice on the left in red, it gets projected up there. It's number 1, so it's one of those up in black and white is the spectra, but the first row 1 is your entire column, red column, okay, and the green would be this other slice. So you get lots of information. Each trace is 30 pixels high, and you get 30 dispersed traces. That's 900 spaxels. That's for the case of NIRSPEC here. Then total, yeah. Okay. And so in the case of MIRI, it's not as clean, and it's even more complex. Just for constraints, just optical constraints. So the MIRI MRS field of view is this here. So the slicer is actually the image is first split into 4 wavelengths domain. Okay, so channel 1, 2, 3, and 4. So they represent different wavelength ranges. Channel 1 being the smallest wavelength, and channel 4 being the highest, the longest wavelengths. I believe I have something, yeah, well, to be very technical, this device here splits 4 colors using 4 dichroics, all right? So you have 4 different wavelength ranges, 4 parallel paths that the light can go through, and then each of those paths gets reflected onto a slicer that I've shown before that slices your image in tiny slices, and in turn, those they go on gratings, and essentially at the end of all this, you get the channel 1, all the slices of channel 1 projected on one half of the first detector, all the other channel on the second half, and so on. And so the thing is, you can observe only a range of color within each channel at a time. So, okay, so there's the short exposure one. Say, imagine you're actually taking images, taking IFU with MIRI. You need 3 different sets of observation. Exposure 1 will cover. So if you look at the plot here where I showed the spectra as a function of wavelength, you have exposure 2 and exposure 3. So, you take 3 shots to cover all of the mid-infrared range. And yeah, that's it. That's all I got for the IFU. I realize now I'm not going into the details of how you should set up a proper observation with the IFU. You usually need to observe a background reference image after having observed your science field, because in the mid-infrared wavelengths, there's a lot of thermal emission from your telescope. I used to have a slide here that's showing this. See it. Well, let me just look if I have it. I think I have it somewhere. Nah, sorry. Oh yeah, here. So yeah, in the mid-infrared, the zodiacal light emits a lot of light, but also the telescope and instrument itself emits thermal light. And so by 5 microns and up, you get some emission, some background that you need to subtract if you do imaging or if you do spectroscopy, you in principle you need to subtract this from your scene. So if you're using the IFU, most likely you have an extended source in your IFU, so there's no good position where to sample your sky and use it to subtract the sky. So you need to observe a separate, source-free region where you get a measurement of the sky background. And so, yeah, so typically IFU with MIRI, you have to devise what's your exposure time for your science and then multiply by 2 because you're going to do the same thing on a reference frame, on a reference field. Right. So let me talk about not TSO. I don't think anyone was interested in TSO, if I'm not mistaken. It's the best modes ever, as far as I'm concerned, but yeah. But we can talk a little bit about the chronography. All right. So Coronography here with MIRI. So there are two technologies to do coronography. So essentially, coronography is when you want to mask a bright star and look for faint objects nearby, like planets. But it could be something else, like masking the core of an AGN to look for the galaxy, the host galaxy. And so the quarter phase mask are there are three quarter phase mask at the bottom left, and those use like uh, I guess the phasing of the light interferometry, interference to suppress light. But you need to position your bright star very precisely at the center of the cross here, and in order to get maximum attenuation. So typically, yeah, um, typically the all of James Webb's coronagraphy modes, they're not as great as the ground-based modes, simply because of the size of the mirror. It's a 6.5 meter, that's big, but not as big as the KEX or the VLTs. So right off the bat, you don't get as much, spatial resolution. Also, we use longer wavelengths, and so the PSFs are bigger. So it's 1 lambda/d is like the best we can do, probably a bit more actually. Yeah, I think I have notes. So the expected contrast for these modes are 10 to the -5 to 10 to the -6. So I don't know if this actually turns to be as we predicted. I haven't followed the results for this. I think it's been good. In fact, if you look at some of the imaging of some planets, they are doing good actually. Not with MIRI, but with NIRCam. Sorry, I don't know what else to tell you here besides what's obvious on the slide. But I think we can go on NIRCam. NIRCam has two different setups. So NIRCam, you go in one of those big squares, black squares at the bottom. You position your star there to do an acquisition of the star, and then you do a blind move into the one of the coronagraphs, like the spots, the smudges at the center, to hide the star, and then you start observations. So it turns out that those the three masks on the left are not really used. I think the best job is when you use the bar. So if you look on the right hand side, you have a bar, a masking bar, and the size you see changes with position. That was to follow the different wavelengths. So if you were observing in the blue, you would go behind the mask where it's very small. If you were observing more in the red with a bigger PSF, you would go a bit on at the center where it's fatter, where the mask is bigger. It turns out the optimal position is actually to go to the smallest mask size, because the mask size is defined by, it's 50% transmission. Turns out we can observe even when it's less than 50% transmission and go more close in the star. Yeah. I think that's all I can say. I will refer you to, the online documentation for more. But like very recently, this mode of NIRCam was able to measure all four planets of HR 8799, the iconic planetary system. So we were not expecting to actually be able to measure the inner one, but we can. So that's good news. And that provides, I should say that why then? But if we're not performing as good as on the ground for in terms of, you know, inner inner angle, um, why bother having such a mode on James Webb? It's important because you can have access to different wavelength ranges than from the ground. So you can have access to all of the 2.5 to 5 micron domain and even to the mid infrared. So that for those planets accessible, it's great information, great new information. But this is the James Webb is not going to, go fishing for new systems. It will essentially characterize existing and known systems. All right, and finally, there's a third mode available for high contrast imaging. It's NIRIS. Uh, it uses a non-redundant masking. So it essentially kicks away 85% of the light, to throw away that amount of light to be able to do interferometry and make fringes and based on and do transform, Fourier transform analysis. And it essentially allows you to recover information at almost half the lambda over D limit. Um, so uh, this can be involving in terms of explaining it. It's essentially each of the pair of openings forms an interferometric pattern, and you can measure its amplitude and thus recover information at that scale. Turns out that we're unfortunately hitting a limit due to the detectors. We're not quite reaching what we expected, which was 10 to the 4 contrast. So about, what is this? 10 to the 4 is 10 magnitudes. We're reaching maybe 7, 8 magnitude. And we're still scratching our head to understand why and how to mitigate this. And I see that it's 15:02. I'm running out of time. So I don't know if there are questions, but I guess I will end here.
Thank you so much, Loïc. Thank you very much for your talk. It's like there are so many details about every single instrument and every single observation mode and every single
Yeah.
like technical thing. Like it's insane to me how scientists and engineers can actually come together and work on such a large and complicated project
Yeah.
to be able to make some of the greatest discoveries in science. I'm always amazed at the level of complexity that is involved with every single instrument. And like honestly, it's it's insane. Like
Yeah, I'm sorry. I wish it were like simpler that you could understand everything in 1 hour. But the reality is, so I think what you could do is you want to approach this with the science you want to do, right? If you have to have a rough idea of what you want. You want spectra, you want imaging. That's a good start. There is, the JDocs, the like the Bible online for documentation that exists, and there are like what do they call them? Like pathways, or starting from very high up and say, okay, which instrument I should use based on what I need. So there are recommendations that you can get, okay, you should use, do you know if you want to use the IFU or just long slit or multi-object? There are, flow charts if you want, or yeah, flows that you can, that exist on the web page to help you out. But I should stress, if any of you guys are serious and have questions, I'm saying for real, you just please contact me. I'll be really happy to guide you and help if anything. So if you have like ideas for a project, really don't hesitate. We can spend an hour on Zoom to discuss your ideas. My role, I was part of the instrument team for NIRIS, but my role continues as a support for the Canada community for Web. So it's actually part of my job description to help you guys. So really, I'm saying it genuinely. If you need help, or even if you're only curious and you want to contact me, we can talk more specifically about what you want to do, and I can guide you and help you. So right now in Canada, we're trying to promote the use of web. So the idea we came up with is to assist like teachers in their class, and they want to do, say, a mock proposal. Like the homework for grad students would be to write a James Webb proposal. Okay, so there are a few classes that do it, and so what I do is I present like everything about web, and then I help them out with the technical aspect to do their proposal. And so with that, last year, one of the students actually who made the assignment, actually, it turned into an actual proposal that was submitted, and she got time on the telescope. So that's a bit of what I'd like you guys to be able to do also, is if you're interested, have an idea, I can help you out, and maybe that could turn out as a proposal that you lead.
Wow.
Yeah.
Thank you so much for your proposition, Loïc. This is really great.
Yeah, no, so if you can spread the word, if you have like fellow students around you that have questions, and they should try to contact me, and it'll be a pleasure. Especially so the next call for proposal is October, it's still many months away, so that's a good time to start doing some first test, and yeah.
Nice. Thank you.
Echo that and just say thank you so much. I know that a couple of us in the Zoom call had to run like right at 3. So
Okay.
yeah, thank you so much for your time and your talk and just being available. I think I actually might take you up on that in the coming months, because yeah,
Yeah.
there's a dream, and it's yeah, just a matter of making it reality. So that would be wonderful. Thank you.
Oh yeah, sure. That'd be great. That'd be great. All right. Thanks for the